Hi everybody, welcome to another video in Calculus section 9.7 plane curves and parametric equation. We focus on the parametric equation, of course that cover the plane curves as well. So what we have here, definition of parametric equation. If we have x equal f of t, a function of t, y equal to another function of t, then f of g together, if they have the same domain, then the collection of all the points x, y given by f of t and g of t is called the plane curve, and the equation x equal to f of t and y equal to g of t are called parametric equation. Usually this is in plural, one for x, one for y. Right. The variable t is called parameters. So the reason that we don't want to call x and y, we call x and y as variables, but we don't want to call t as variable. We call that something different names, like parameters, just to distinguish that the fact that x and y are on the plane. So xy coordinate system still x and y. T is the parameters. We don't plot t on this coordinate system. Right. So that's the difference between the parameters and a variable. Right. Let's look at the equation in the sample. Parametric equation. Let's say we have x equal to 2t squared and y equal to 3t. First of all, we try to graph this. So graph this is easy. We just make a table, put x and y in it. Find x and y. X is equal to 2t squared. Y equal to 3t. Right, let's just t go from -2 to 2, so let's choose -2, 0, 1, and 2. Right, put -2 here, that is 8, and -2 times 3 is -6. Put -1 here, -1 squared is 1, times 2 is 2, and -1 times 3, t equal to 0, t equal to 1, and t equal to 2. Right. So let's plot those points. 0, 0, -2, just ignore, 2 and 3, x equal to 2, y equal to -3, and positive 3. 8 and 6. By the way, it stops at this. Those are the endpoint. 8 and -6, and 8 and 6. Those are the endpoint. Right. So actually, it is a parabola. Right. And furthermore, t go from -2 to 2. So at t equal to -2, we start at this point. This is where we start. This is where it ends. And we go on this path. If we want to graph in a calculator, hit mode, go to number 2 actually, parametric form, right? And then y equal to, we can plot x1 is x is equal to 2t squared and y 3t. Because we hit graph, that's what we have. However, need to go to Windows because t goes from -2 to 2. Let the increment be 0.1, so it increase by 0.01. That's good enough. So then we have the parabola that go like that. Right. So that's good to know. Can we turn this into a rectangular form though? Well, that actually should be very simple. X equal to 2t squared, y equal to 3t. Now if we can somehow eliminate t, that would be great. Like square both sides and subtract, that certainly works. But I use substitution instead. If I divide by 3, so for t is equal to y divided by 3. Right? So for t, y divided by 3. And I can substitute that into this t. So we have x equal to 2 y over 3 square. So that gives us y square over 3 square is 9. Or we say x is equal to y square, 2y square over 9. Right? Not quite. I mean, it's right, yes, but it's not done. Notice that t is between -2 and 2. Here we have what? 3t. So if we multiply everything by 3, multiply by 3, we should have -6 less than equal to 3t less than equal to 6, and 3t here is y. So when we write the equation, make sure we also have to write y between 6 and -6. Yeah, we have to write that out as well. So the parametric equation, even when we write like this, we still didn't know the actually, we just know the curve. We don't know the actual path of the curve. It's not going that way or that way. So that's one advantage of parametric equation. It will tell us where it starts, where it stops, and the direction of moving as well. Right. So this is one way to eliminate the parameters. Another way to eliminate the parameter is this. Find the rectangular equation of the curve given by this. Of course, if we want to solve for t, divide by a, take the inverse. That sounds like a lot of work, and that's certainly complicated. But let's just rewrite this. X equal to a cosine t, and y equal to a sine t. Right. What's that? Let's keep this in radian. All right. Let's see. A is 5 cosine t. X is 5 sine t. It goes from -infinity to -infinity. So let's say from -100 to 100. I don't want to, cannot put infinity in there. Increment is 0.1. Right, let's see. So what we have is, of course, it just goes around, 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 around. So it is a circle, by the way. I shouldn't put 100, that's too much. So it is a circle, because both of them equal to 8. Now, notice, if we solve for cosine of t, we just divide by a on both sides. Right? And then let's square both sides. So why do we do that? Because when we do that, if we add side by side, cosine square plus sine square is equal to 1. And the square, I will break it up as x squared over a squared, y squared over a squared equal to 1. And this is the equation in rectangular form. It is an ellipse. We go left and right a unit, up and down a unit. Negative a, and we draw a box. box. And the ellipse will fit inside that box. Since both of them equal to A, it is a circle. Of course, I could draw a circle better than this. And by the way, the reason we need to draw this out so we can say the limit for x between negative a and a, the limit for y between negative a and a as well. Right. So two ways to eliminate the parameters. One way to solve for that parameters and substitute into the other one. And if we see sine cosine, do this because cosine square plus sine square is 1. So this is one way to do that. Right. Next, for this equation, find a rectangular form for this one. So we have x and y. So either we solve for y or we solve for x. And just look like this one is easy to solve for. To solve for t in y and solve for t in x. I think it's easy to solve for t here. So if we take this equation and we solve for t by plus 2 on both sides. And then we can substitute into x. Into the equation x, t is equal to y plus 2. So we have x equal to 2 plus 3 times t. The t is y plus 2. And multiply it out, x equal to 2 plus 3y plus 6. Or x equal to 3y plus 8. But notice every time we do that, this is the whole line. This is only a line segment, so we have to solve for t between 0 and 2. But we need to have t minus 2. So originally 0 between 0 and 2. If we subtract 2 on both sides, actually everywhere, we have negative 2 less than t minus 2 less than 0, and t minus 2 is y. So y between negative 2 and 0. Right. So those are the two ways to eliminate the parameters and turn that into rectangular form. One of which, solve for t, substitute in the other equation, and the other is if we have sine cosine, square both sides. Cosine square plus sine square is 1. Right. Next we have an application, projectile motion. Actually, only this example is projectile motion. This one is not. The next one is not. Right. So in calculus, it can be shown that in parametric equation, the path of a projectile fly at an angle theta, so like hitting a golf ball 45 degrees off the ground, for example, with initial speed v0, and h is the distance above the ground. If it is a golf ball, more likely that distance is very small off the ground. Right, and the equation will be given by this, where g is acceleration due to gravity, 32 feet per second square, or 9.8 meter per second square. And usually acceleration in that case is, we have the negative because the gravity points down, right? Right, so we have those two, x and y. Now suppose that Jim hit a golf ball at initial speed of 100 feet per second. So what we have is v0 is 100 feet per second at the angle 45 degrees. So we have theta is 45 degrees as well. Find the parametric equation that describes the position of the ball as a function of time. So that's easy. We have x and y like that. So x equal to v0 cosine of theta times t, and y is negative 1/2 g of t square plus v0 sine theta t plus h. Right, initial speed is 100 feet per second. cosine of 45 degrees t, and y negative 1/2. G is, let's use actually feet per second, right? So we have to use 32 t square plus v initial speed 100 sine of 45 degrees times t plus h. Suppose we just hit the ball from the ground, 0. Right, and then we can say 100 cosine 45 degrees is square root of 2 over 2, and y equal to negative 1/2 times 32 is 16 t square plus 100 sine 45, once again square root of 2 over 2 t. Right, simplify this, we will have x equal to 50 square root of 2t, y equal to negative 16t square plus 50 square root of t square root of 2t. And then all we know is that this function t is going to be positive because time cannot be negative. Right, so that's what we have. Next, how long was the golf ball in the air? So how do we do that? So let's take a look at this. Initially, we hit the golf ball from the ground level. When it hit, it will travel in parabolic path and will hit the ground at some point. What's so special about these 2 points? Well, it's on the ground, right? If it's on the ground, then y must be equal to 0. And so pretty much we will let y equal to 0 and we calculate 2 instants. One of them is where it hit and the other one is where it hit the ground again. When the golf ball is hit by the club, and then where the golf ball hit the ground. And so when both of those times y equal to 0, so pretty much we just need to find y equal to 0. Right. So how long was the golf ball in the air? So meaning that is so when the ball hit the ground is y equal to 0. So the ball is at ground level. So in that case, we let y equal to 0. So we solve for 2 values for t. Right, this is easy. We can factor out t, right? We have negative 16t plus 50 square root of 2 equal to 0. So we have t equal to 0 or this equal to 0. Move that over, divide by negative 16. Right, so we have 50. By the way, let's clear the equation. And change the windows to something standard, like right. And we have negative 50 square root of 2 divided by negative 16. We have about 4.41 something. So in terms of the golf ball, when it travel in the air and hit the ground back again, initially t equal to 0 when it starts to move, and 4.41 is when it hit the ground. Next, when was the ball at the maximum height? Determine the maximum height of the ball. So how do we do that? Right. By the way, assume that there's no air resistance, or there's no friction between the golf ball and the air, which of course in real life there's always friction. But let's assume that there's no friction. So how do we determine the maximum height? So what is the characteristic where the ball is at the maximum height? So the ball travel like this. It is say that it is parabola or the parabolic path, right? And it is. So if we have this, then the line of symmetry will be right in the middle. The vertex will be on the axis of symmetry. So we know where the ball is at the maximum height. That's easy. Just will be halfway through the interval, right? By the way, the reason it is halfway through the interval because we know both of them have y equal to 2. They have the same y values. So cut that in half. We should have where it is the maximum height, because it is the axis of symmetry. We have to have the same y values. So the line in the middle will be the line of symmetry, and the line of symmetry will go through the vertex. So the vertex will be at the middle of this. So when the ball is at the maximum height, well, the ball is at maximum height, is halfway of its path. Meaning that the time is equal to just that divided by 2. That's 2.21 second. So after 2.21 second, the ball is at the maximum height. The golf ball is at maximum height. And in order to find the height, maximum height itself, just going to substitute 2.21 into this equation for y, negative 16, 2.21 square plus 50 square root of 2, 2.21. So what I do is actually it should be 4.42. Yeah, if I round that up. Yeah, so I will take this divided by 2 and I store into x. Store into t, even better. And now we have the equation negative 16t squared plus 50 square root of 2 times t. That's 78.125 feet. So the maximum height is that. But the next one is a little more interesting. Determine the distance that the ball travels. Well, if we just want the answer, that's very easy. We know the ball travels 4.41. All we need to do is just substitute in for x, and that will be it. That is the easy answer. Distance travel 50 square root of 2 times the time. So that whatever it is. What I do instead of doing that, let's just look at this equation in general. Try to derive the formula in general. It will be a lot better than trying to estimate the values here. Right? So let's just look at the equation this way. X equal to V naught cosine theta t y equal to -1/2 gt square plus v naught sine theta t. I will let h equal to 0. Assume it hit off the ground. Now, we will let this equal to 0. When we do that, this is give us the time where the object at the ground level time. On the ground, either before it hit and after it hit. Yeah, t equal to 0 and t equal to something. So I just factor out the t at -1/2 gt plus v naught sine theta equal to 0. So it's easy, t equal to 0. That part is easy. And then the other part is -1/2 gt plus v naught sine equal to 0. Now if we want to solve for t, move that to the other side. And then what? Divide by -1/2 g. Divide by -1/2 is multiplied by -2. So negative and negative cancel out. So just say v naught sine theta g divided by 1/2 multiplied by 2. Right, so give us the time is equal to 2 v naught sine theta over g. Now we will substitute that into this t to find the distance that actually travel, right? So we have x equal to v naught cosine theta. T is going to be this, 2 v naught sine divided by g. Combine the top, we have 2 v naught square sine and cosine over g, and we have 2 sine cosine, that gives us sine of 2 theta, right? So v naught, and that gives us sine of 2 theta divided by g. So this is called the range formula. That distance. Usually, it is useful in the artillery, so we can know how far a cannonball will hit the ground again. So usually, if in the cannonball we know the speed of the cannonball as hit the cannon, we just need to identify the angle. So what angle should we aim so it will hit the ground? Right, so in this case we have 45 degrees, which gives us the maximum height. So if we want to hit at the maximum, the maximum distance, aim at 45 degrees. Because sine of 2 times 45 degrees, sine of 90 degrees, sine of 90 degrees equal to 1. So the maximum range is at 45 degrees, which is equal to v naught square divided by g. So in this case, we go back to our problem. And we have x equal to v naught square sine of 2 times theta divided by g. V naught 100 feet per second square sine of 2 times the angle divided by G32. So 100 square sine of 90 degrees is 1. I don't even need to do that. Divided by 32. So at 312.5, a reasonable fit. Because if we do that, we should get the same thing. 50 square root of 2 times 4.0 times that. Yeah, it should be the same. But we have the range formula, which is actually then I'll be very useful there. Right, next. This is not a projectile motion, it's just motion in general. Tanya, who is a long distance runner, 6 miles per hour, that's actually very fast for long distance running. 2 hours later, you leave your house and drive at 35 miles per hour. How long will it be before we catch up? So first, for Tanya, 7 miles per hour. So what is the distance? The distance is S. 7 miles per hour times time, right? After 1 hour, 7 miles. 2 hours, 14 miles. 3 hours, 21 miles. Right, next. That is, and then after that, you now we leave the house and do that. So how do we write the speed? So this is 40 greater than or equal to 0, right? Now, next, we leave the house, but 2 hours later, right? And 35 miles per hour time. I will not use time because that time is down from 0. So let's use a different time. Anyway, just use U as well. Let's use U, where U is time, but it is 2 hours later. U is 2 hours later than T. Two hours later than T, meaning that U is T minus 2. T is more than 2. So we substitute back in here. S is equal to 35. U is equal to T minus 2. In this case, T is greater than or equal to 0. So this is the speed of us. I mean the distance that we travel. And this is the distance that C ran, right? Because the time here is 2 times later, so they have to be less than 2, less than that time. So that's what we have. And when we catch up, just let them equal each other. 7t equal to 35t minus 2. And then we have 7t equal to 35t minus 70. Move the 70 and move the 70 on the other side. Subtract 70. So we have negative 28t equal to negative 70. Right? Subtract 35t on both sides and then divide by negative 28. So 70 divided by 28, 2.5. and that will be hours. So 2.5 hours later, we will catch her if we start 2 hours later. So in total, she run for 4.5 hours. Well, that is very good for a person that can run 4.5 hours at a constant speed of 7 miles per hour. So that's more like, of course, a marathon is less than that. Right. So next, we have more example. Now, earlier we have parametric equation. We write that in rectangular form. Now, can we do that in reverse? If we have the parametric equation, if we have equation in rectangular form, can we write that in parametric equation? Well, actually, it's not that bad. We have x equal to y squared plus 5. Right? So in that case, why don't we just say if we let y equal to t, then of course x is equal to y squared, which is t squared plus 5. Yeah, that is the equation. So we just say x equal to t squared plus 5, and then y equal to t. It is much better to let y equal to t than to let x equal to t. And in that case, we change t can be anything. Right? T, just real numbers. So that's one way to do that. The other way is that, why don't we just let y squared be t? If we let y squared be t, then x is equal to what? T plus 5. So we could write the equation as x equal to t plus 5, and take the square root on both sides. Y equal to square root of t. The only problem is when we write like this, t cannot be negative. If t is negative, it is undefined. Right. So be careful with that. So that's why it is better to write just in this form. Right. So next, find the parametric equation for the line segment 0 to 1 and 0, 1 to 2 and 3. So if we just try to plot this, okay, 1, 2 and 3. One, 2, 3. Okay. Go from the 1, 0 and 1, and then 2 and 3. So we're talking about that segment. Just a line segment. It doesn't matter. We go from here to there or there back to here. Right. So how do we write that? We know x go from where? 0 to 2, and y go from 1 to 3. Right, so just make a table here. And y, x first. And then another table for y. Right. Now, we can choose t to be anything. Let's say initially we set t equal to 0 and then later on t equal to 5. If that is the case, perfectly fine. But let's say at t equal to 0, we have this point. At t equal to 1, we have that point. And that's what we strictly just choose between 0 and 1. When t equal to 0, x is equal to 0 for this case, and y equal to 1. When t equal to 0, y is equal to when t equal to 0, y equal to 1. Sorry. T equal to 0, x is equal to 0, t equal to 1, x is equal to 2. Next, t equal to 0, y is 1, t equal to 1, y 3. Alright, so we have that. This is just a straight line, so we can just write the equation is y equal to mx plus b in general. That's terrible. Where the slope is equal to y2 minus y1 over x2 minus x1. If that is in relation between x and y, but now we have x and t, so we do the same thing. The slope y2 minus y1 over x1 minus x2 minus x1, so it's 2. So the equation is y equal to mx plus b. We know that, we'll worry about that later. We know slope is going to be 2. Sorry. X and then t. Sorry. T is the independent variable. X is dependent variable. So that's what we have. Now we have the point 0, 0. When in x equal to 0, when t equal to 0. So b is equal to 0. So bottom line is we have the equation is x equal to 2t. Next, on this one, do the same thing. M equal to y2 minus y1 over x1 minus x2 minus x1. So 3 over 1 is 2. The equation y depends on t, where the slope is 2. Now at the point 0 and 1, y equal to 1, where t is equal to 0. So b here is equal to 1. So the equation is y equal to 2t plus b, 2t plus 1. So we have x equal to 2t, y equal to 2t, where t between 0 and 1. So this is the parameterization or the parametric equation of that line. Right, so that's good and all, but that sounds like a lot of work. Now, if we go back to vectors, let's say the coordinate of this point is A, the coordinate of that vector is B, and we say the vector AB is equal to B minus A. That's what we have earlier, right? That's what I want to write for the note. That means if we want the vector AB, if we want the point B, it's going to be AB plus A. So now, meaning that, say if we don't want the point B and we want the point C somewhere in here, let's say the point X there. We start from the point A and then plus the vector AB times t. And when t equal to 0, we're at this point. When t equal to 1, we're at that point. Yes, so this is a better way to parameterize the line. Just take the initial point plus t times the vector connecting them. So if we're going to use that formula here, once again, A plus t, AB, vector AB, t between 0 and 1. Right. So, start from the point A, which is 0 and 1. Vector AB is point B minus point A. So I have 0 and 1 plus t times the point B 2 3, subtract point A 0 1, so we have 0 1 plus t times, subtract this, we have 2 and 2, multiply, and we have 0 and 1 plus 2t comma 2t, and add the component. 0 plus 2t is 2t, and 1 plus 2t. Right, so if we want to parameterize the line segment, initial point plus t times the vector connecting them, and when we do that, we have x equal to 2t, y equal to 1 plus 2t, and t is between 0 and 1. Right, so that's pretty much it. Simple enough. Right, so keep in mind this is the way we parameterize a line segment, to turn a line segment into a parametric equations. Next, parameterize this, meaning that I will find a parametric equation for that curve from 0 to 2. Well, this is easy. We have y equal to x squared plus 1. Why don't we let x be t, and then we have y equal to x squared plus 1 t squared plus 1, and then x go from 0 to 2, and t is between t is equal to x, so t is between 0 and 2 as well. So we have the parametric equation x equal to t, y equal to t squared plus 1, and where t is between 0 and 2. Right, so that is we turn an equation into a parametric equation. That process is called parameterization. Now, the next part is how do we parameterize an ellipse. By the way, we have the polar coordinate before, right? X equal to r cosine theta, y equal to r sine theta. Of course, we have that. Right, now, let's look at this. Usually, the standard polar coordinate, we start from this axis and we go counterclockwise, right? That is the standard. And one revolution is 2 pi. Right, so keep that in mind. The standard is going from positive x-axis or to the y-axis in that direction. And it takes 2 pi, from 0 to 2 pi to go travel one complete revolution. Right, now, this is a little more advanced. Suppose the motion around an ellipse clockwise, this is clockwise, begin at 0 and 4, require 2 pi second for one complete revolution. Right, so let's start with x squared, y squared equal to 16 equal to 1. One thing we know, something equal to 1 is always cosine square plus sine square is equal to 1. We always have that, right? Now, naturally, we will let one of them is equal to cosine square and one of them is equal to sine square. But the key is, which one which? Do we let x square equal to cosine square, or we let x square equal to sine square? Now, I asked you that question earlier. Standard polar coordinate go from positive x-axis counterclockwise, x go to from the x to the y-axis pretty much, and x standard polar coordinates is r cosine theta, right? And y is r sine theta. So if we want to go counterclockwise, x equal to r cosine, y equal to r sine. That means the cosine we associated to x and the sine associated to y. But that is not what we want. What we want is clockwise. So in that case, we will let x squared equal to sine square, right? So instead, we match x squared with sine square, make them equal, and cosine square equal to y squared over 16. right? Then take the square root on both sides. X equal to sine t. Multiply 16 and take the square root, so y square equal to 16 cosine, so y equal to square root of that before cosine t. That's it, pretty much. Right. So solve for y square. Y square is equal to 16 square. 16 and cosine square. So take the square root. Y equal to 4 cosine t. Now, we need to check though. By the way, this is an ellipse. Below the x square is 1. So we go 1 unit left and right. And then 4 unit up and down. So the ellipse will go in this direction. So we have the shape of the ellipse, we have the equation, which is good. Now just to make sure that it actually go clockwise, we can check that with the calculator. But it takes 1 revolution, right? It's 2t, 2 pi. So t between 0 and 2t, 2 pi, sorry. So t is between 0 and 2 pi. And so we can say it is between 0 second and 2 pi second. So it takes 2 pi second to travel 1 revolution. Now the moment of truth. Just enter this in the calculator and make sure it works. Parametric equation, that's good. In radian, also good. Now y equal to sine t and y equal to 4 cosine t. Change the windows though, from 0 to 2 pi. And let's say that we have pi divided by 50. So for every pi, it will graph 50 points. Get very small number. Right, it will graph. It start from that point, going clockwise, and get back to that point, which is good. And that's exactly what we have. Now, let's say if we want clockwise, but we start at this point, what do we do? In that case, just change this from pi over 2 to 2 pi plus pi over 2. If we want to start this point and go clockwise, just change that index. I mean change the parameters, right? If we want to graph like this, but instead we go from pi over 2 to pi over 2 plus 2 pi. You see, it will start this point and still go clockwise and get back to that point. Right. So if we want clockwise, x go with sine, y go with cosine. If we want counterclockwise, x go with cosine, y go with sine. The standard one. Right. But in this case, we have x equal to sine t, y equal to 4 cosine t, and t, because start from here, between 0 and 2 pi. So the way I remember this is it always rotates from the cosine to sine. So if we let x go to y, go from cosine to sine. If we let y go to cosine and x equal to sine, it will go from cosine to sine. That case will be clockwise. So always go, it will take from the whatever we let equal to cosine equal to whatever we let equal to sine. In that direction. Now this one, the motion of that ellipse, still ellipse, something. X square plus y squared over 16 equal to 1. We still have that. But this time it had begin at 1, 0 and require 2 seconds for one complete revolution. So we have to do it a little bit different here. Let's still find out. Right. Once again, we will have cosine square plus sine square is equal to 1. Now we just match. One of them is cosine square, one of them is sine square. And this time counterclockwise. So we go from the x-axis to the y-axis. So we go from cosine axis to the sine. So x should go with cosine. And y square over 16 equal to sine square. Take the square root on both sides, x equal to cosine t. Multiply 16 y square equal to 16 sine square. Take the square root on both sides, y equal to 4 sine t. Now, what we want originally, if we travel one revolution, it is going to be what? 2 pi, right? But now if we only want one revolution in 2 seconds instead. So how do we do that? What do we do? Right, if that is the case, we need to divide by pi on both sides. So we have 0 between t over pi between 2. If we write like that, it will be between 0 and 2. 0 and 2 seconds. Now, if we do that, this have to be some new variable. So let that be s, for example. If we use s, then s is between 0 and 2. Right? So, but if s is equal to t over pi, so what is t equal to? Pi s. Right? Then we can substitute that into the equation. So the equation now is x equal to cosine of t. T is pi s. And y equal to 4 sine pi s. S between 0 and 2. Alright, that's good. Finally, if you don't want to use s, you want to use t, perfectly fine. Just change it back to t. Now, let's try this. Parametric form, Radian, which is good. Equation, cosine t for x, cosine pi cosine of pi t, and then 4 sine pi t. Right? Yeah, of course you can just keep the answer in s, but I just want to switch it back to t. It's usually parameters we use t. The windows only go from 0 to 2. And let's say it goes h1 0.1 h. It goes from this point will counterclockwise, so which is actually good. Because when t equal to 0, put 0 in here, we have the point x is equal to cosine of 0 and y is equal to sine of 0, 4 sine of 0, which is 0. So indeed we start from this point, and we have pi t and pi t. Now let's say if we want to start at this point instead, well, in that case we just want to shift the t. That point is at t equal to pi over 2, so we just go from pi over 2 and then yeah, we have to go back in here and shift that from this step. Actually, if we want to graph from that point, this is t equal to 0 at this point. This go back to here is 2, so 0. Back to here is 2, so 0, 1. Back here is 2, so this is 0.5. So if we want to graph it at 0.5 to 2, if we start from this point to go counterclockwise. If we want to get back into one complete revolution, 2.5, now it will start from that point going counterclockwise. Bottom line is you go from the cosine to sine. So if it is clockwise, x go with sine, y with cosine. If it is counterclockwise, x go with cosine, y go with sine. Right? And then normally it is 0 to 2 pi for one complete revolution. If we want more or less, we have to turn that into that number and change the variable to accommodate that. And finally, we go back to t if we want to. Right, so that is parameterize an ellipse. A circle would be the same way. Right, next we're just going to give you that. So if a circle rolling around, if we mark one point on the circle, let's mark this point on the circle and rotate. When it rotates, just keep track of that point. This will be the path that it travels. And to parameterize that, we're going to use this equation. Well, because the book has this example, so I'm just going to put that here. But that's all I want to cover in this section 9.7. As always, thank you for watching and see you in another video in pre-calculus.